All right, today we're going on a fascinating journey. We're going to take one of the most common, unassuming rocks on the planet and watch it transform into one of history's most important and frankly magical building materials. This is the story of lime.
You ever find yourself staring at a picture of the Roman Colosseum or maybe an ancient aqueduct and think, how is that still standing? What on earth were they using to hold all those stones together? Well, long before modern cement was even a thought, the answer was almost always this one incredible material.
So, here's our game plan. We're going to follow the entire life story of this material. We'll start with the raw rock, watch it get forged in fire, and then see it literally brought to life with water. We'll even check out the different personalities of lime before we wrap it all up. Our journey starts right now.
Okay, first things first. Every great story has a beginning, and for lime, that story starts deep inside the earth with a rock you have definitely seen before.
Meet the star of our show, limestone. You know, chemically speaking, it's called calcium carbonate, but for us, it's just the essential starting block. Every single type of lime we're going to talk about today begins its life right here as this simple rock.
And this is where things get really dramatic. That simple rock is about to go through a trial by fire. Literally. It's a process that's going to completely rewrite its chemical identity forever. The process itself sounds pretty straightforward, but it's incredibly powerful. First, you dig the limestone out of the ground. Then, you put it in a kiln and you bake it at insanely high temperatures. We're talking 900 degrees Celsius. What comes out of that intense heat is a totally new, highly reactive material called quicklime.
Let's geek out for just a second and look at the chemistry. You start with your limestone, CaCO3. When you hit it with all that heat, the chemical bonds actually break. A gas, carbon dioxide, that's the CO2, is released and floats away, leaving behind just calcium oxide, or CaO. And that is our quicklime.
And this whole process has a really cool name, calcination. It's a fancy term, but all it means is you're cooking a solid material to force a gas out of it. This is the exact step that turns a stable, boring rock into an unstable, chemically hungry powder.
So, we've made this super reactive quicklime. The thing is, you can't build with it yet. It's way too aggressive. You could almost say it's thirsty. So the next big transformation is all about quenching that thirst to make it something we can actually use.
Now this part is just pure chemistry in action. You take that quicklime, you carefully add water, and boom, you get an instant, powerful reaction. It gives off a ton of heat, so much that you get these big clouds of steam, and those hard lumps of quicklime just crumble into this fine, fluffy powder. This new stuff is called hydrated lime.
And here's the science behind that little explosion of energy. Our quicklime, the CaO, literally combines with water, the H2O, to become a brand new molecule, calcium hydroxide, or CaOH2. And all that heat, that's just leftover energy from the reaction. This is the final product that builders have used for thousands of years.
This second key process is called slaking, or hydration, which makes sense, right? So let's keep it straight. Calcination is using heat to kick out carbon dioxide. Slaking is using water to create the final stable building material. Two transformations, that's it. From a simple rock to a wonder material.
So let's just put these two side by side to make it super clear. On one side, you have quicklime. Think of it as the raw, unstable ingredient that desperately wants to react with water. On the other side, you've got hydrated lime. This is the finished product. It's stable, it's safe to work with, and it's ready to be mixed into a mortar or plaster. The takeaway is simple. You can't build with quicklime, you build with hydrated lime.
Okay, so now we get the basic journey, right? Rock becomes powder. But here's the twist. It turns out, not all limestone is created equal. The actual makeup of that original rock is what determines the kind of lime you get in the end, and what job it's going to be good for.
See, it all comes down to purity. If you start with limestone that's super pure, like more than 95% pure, you get something called fat lime. It's great for things like wall plasters. But if your rock has some clay impurities mixed in, that's when you get hydraulic lime. And those little bits of clay give it a superpower. It can actually harden underwater. That's why it's perfect for building bridges or foundations. And if your rock has too many impurities, well, you get poor lime, which, as the name suggests, isn't great for much. The original rock really does decide the final purpose.
Whew, we have covered a lot of ground, haven't we? We followed our humble little rock through some pretty intense transformations. So let's do a quick recap of that whole amazing journey.
So let's just boil it all down. It all starts with a rock, limestone. You use heat to drive off a gas and create reactive quicklime, that's calcination. Then you add water to create usable hydrated lime, that's slaking. And remember, the purity of that very first rock is what dictates whether your lime is good for a fine plaster wall or a massive stone bridge. It's an entire family of materials from just one source.
And that really brings us to our final thought. For thousands of years, this simple, natural cycle has given us some of our most beautiful and long-lasting buildings. So, as we look for smarter, more sustainable ways to build our own world today, it really makes you wonder, right? What other secrets could this ancient technology, born from just rock, fire, and water, hold for our future?